Any homework problems or other problems in the book that you want me to solve or try to solve?
Good morning, Professor.
Morning.
Professor, can you please go over question 11 from page 89?
Okay. Let's take a look. Ah. So these are problems from section 3.1. And question 11 says, prove that if M has one primitive root, then there are exactly C of M primitive roots. So maybe before I do that problem, as kind of a warm-up, I'll do a couple of the earlier problems in that section. So I had assigned actually 1 through 9, 11, and 13. So let me look at number 3 first. So number 3 is to prove that 2 is a primitive root modulo 101, which is a prime number. And so if we look at Z mod 101Z, that's all the congruence classes mod 101. And if I look at that star, that means the non-zero congruence classes. This is a multiplicative group of order P minus 1, which is 101 minus 1, or 100. So this is a group of order 100, and by Euler's theorem, A to the 100 is congruent to 1 mod 101 for all integers A, which are not congruent to 0 mod 101. Any number that's relatively prime to 101, if you raise it to the 100th power, you get 1. Moreover, for every A not congruent to 0 mod 101, the order of A, which is the smallest positive integer k, such that A to the k is congruent to 1 mod 101, is a divisor of 100, which means k, what are the divisors of 100? 1, 2, 4, 5, 10, 20, 50, and 100.
You're missing 25, Professor.
Sorry? Oh, and 25, thank you. 25. So there should be 9 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So if a number to the power 1, 2, 4, 5, 10, 20, 25, or 50 is not 1 mod 101, then it must have order 100 and be a primitive root. So let's look at the powers of 2. 2 is relatively prime to 100. 2 to the first power is 2 mod 101. 2 squared is 4. 2 to the fourth is 16. 2 to the 5th is 32. So none of them is 1. What about 2 to the 10th? 2 to the 10th, that's a little harder. Let's see. 2 to the 6th is 64. 2 to the 7th is 128, which is the same as 27 mod 101. 2 to the 8th is 2 times 2 to the 7th, which is 54. 2 to the 9th is 2 times 2 to the 8th, which is 108, which is 7 mod 101. So 2 to the 10th is 2 times 2 to the 9th. That's 2 times 7, that's 14 mod 101. 2 to the 20th, that's 2 to the 10th squared. That's 14 squared. I think if you square 14, what do you get? 196? Is that right? I think so.
Yes.
Which is the same as 96, which is also the same as minus 5 mod 101. So 2 to the 25th, let's see, what is 2 to the 25th? Well, I could
Professor,
just,
196 is not 95 and mod 101.
Yeah.
sorry?
186 is not 95
Yeah.
in mode 101.
Oh, sorry, it's minus 6, is that right? It's 95, thank you, which is minus 6
Mhm.
modulo 101. 225, let's say that's 2 to the 5th times 2 to the 20th. 2 to the 5th, that's 32 times minus 6. What is 32 times minus 6? 8 minus 198? No. 6 2s are 12 minus 192, which is the same as 10 mod 101, right? 2 to the 40th is 2 to the 20th squared. That's minus 6 squared, which is 36. And the last number, oh, I don't even need to check 2 to the 40, so forget that. But 2 to the 50, that's 2 to the 25 squared. That's 10 squared, which is 100, which is minus 1. So if I check 1, 2, 4, 5, 10, 20, 25, and 50, none of those 8 exponents has the property that 2 to that number is congruent to 1 mod 101. So 2 must have order 100. So just by this process, just doing some calculation, 2 is a primitive root mod 101. I mean, that's one way to solve the problem. There can be other ways, but this is certainly one way, and I just wanted to find a solution. Okay. Any questions about that? And then problem 4 is to find the index of 27 with respect to the primitives root 2 modulo 101. So to say that k is the index of 27 to the primitive root 2 means 2 to the k is congruent to 27 mod 101. Because 2 is a primitive root, every number not divisible by 101 is going to be a power of 2 mod 101. So we want to find the k that works. I don't know. Any suggestions about what to do? I mean, on the previous page, for various values of k,
Professor,
we did calculate 2 to the k mod 101.
Professor.
Yes,
So the way I did it is by first look, I look if I add 101 plus 27, I get 128, and 128 is actually a power of 2, so it should be 2 to the 7.
oh, okay, so that's very clever. 101 plus 27 is 108,
128.
which is 2 to the 7th. No, is that right?
Yes.
32, yeah, 2 to the 7th. So if you have some good arithmetical sense, this says 2 to the 7th is congruent to 27 mod 28. So the answer is 7.
I had an issue with the following one, with the next question that says something modulo 19, I think, and 19 modulo 101.
Uh-huh, okay.
That one I got stuck. I didn't know what to do.
So let's say k is the index of 19 with respect to the primitive root 2. So we want to find the k where 2 to the k is congruent to 19 mod 101. And a clever trick that worked here doesn't seem to work here right away, does it?
Yeah, it doesn't work. Like I just start adding 9 and 19, and you don't find like something power of 2.
Yeah. So let's see. From the previous problem, I had calculated some powers of 2. So when k is 1, 2 to the k is 2. When k is 2, 2 to the k is 4. For 3, it's 8. For 4, it's 16. For 5, it's 32. For 6, it's 64. For 7, you just calculated, it's equal to 7. Sorry, 64, 120 is 27. 2 to the 8th, we got 54. 2 to the 9th was 7. And we also did 10, 20, 25, 50, and 2 to the 100, of course, is 1. 2 to the 10th was 14. 2 to the 20th was minus 6. 2 to the 25th was 10. And 2 to the 50th was minus 1. Well, I don't know. I mean, in the worst case, you just start calculating all the powers of 2, but you might have to calculate a lot of them. Yeah.
There is not an efficient way to do this, like without having to do trial and error.
I'm trying to see. So 19 is congruent to 120 mod 101. Is that right? I think so. And
Yeah, that's correct.
that's 6 times.
Professor, sorry,
Yeah.
sorry for interrupting you. There's an student that is saying that if you can let him in the class, like he's waiting in the waiting room.
I'm sorry, I just didn't hear what you said. It was very soft. Can you
There's
repeat it again, please?
Yes, no problem. There's a student in the waiting room that is saying if you can let him in.
Oh, thank you. Sorry, I didn't notice. Thank you very much.
No problem, no problem.
Okay, so 19 is congruent to 120. which is 6 times 20, right? Which is 6 times 2 times 10. Is that correct? Which is -1 times -6 times 2 times 10. Is that correct? And -1 is 2 to the 50th. 2 is 2 to the first. Sorry, I want to look at this. -1 is 2 to the 50th. -6 is 2 to the 20th. 2 is 2 to the first. 10 is 2 to the 25th,
It works. Mhm.
right? So this is equal to 2 to the 50, 70, 71, 71, and 25
96.
is 96 mod 101. So the index of 19 with respect to the primitive root 2 is
Oh,
96.
That makes more sense. That's a lot easier.
It's easier, Professor. Can you leave it a moment so I can write it down?
Well, but it's easier, but you have to be lucky, right? I mean, I was lucky. I made this list and then I couldn't work with 19, so I tried 120 because they're the same mod 101. And this had a lot of factors and I tried to factor it into pieces, all of which were in this right-hand column. So, you know, so as in many fields of human endeavor, it's good to be smart. It's also good to be lucky. So I think here I was just lucky. Of course, the problem is if you try to do this by exhaustion, taking every power of 2, you might have to go like 96 times. That's maybe a little bit too much. Probably half of the time you would have gotten to like -19, and then you could have multiplied by -1. So that wouldn't have been so bad, right?
Wait, Professor,
Yeah,
you will not put something like this in the exam, right?
no, because I
Thank you.
can't, you can't give a problem where you either have to have 3 hours to do it or, you know, be lucky. So no, I would not give this kind of problem.
Thank you.
I mean, I might ask you to calculate an index, but it would have to be an index that it was easy to calculate.
Yeah, maybe mod 13 or something like that.
Well, whatever, something, yeah. But it wouldn't be something like this complicated. All right, so this is a little bit about primitive roots and indices. But what about problem 11? That's the one that started this discussion.
Wait, Professor, real quick before you turn the page.
Sure.
For number 4, you meant to write mod 101, right? Not mod 28. All right, cool.
you.
Just making sure.
Exactly, thank you. Okay, so let's look at number 11. So we need to suppose that let G be a primitive root mod M. So what that means is Z mod MZ, that's the ring of congruence classes mod M. It's generally not a field unless M is a prime, but in any case, Z mod M star, this is all congruence classes A plus MZ, where A and M are relatively prime. This is a multiplicative group. Of order exactly how many integers from 1 to m are relatively prime to m, and that's phi of m. So m is not, might be a prime, but not necessarily. So this means that phi of m is the smallest positive integer such that g to the phi of m is congruent to 1 mod m. And also, if a and m are relatively prime, then a is congruent to g to some power mod m. Right? That's what it means to be a primitive root. Every congruence class relatively prime to m can be represented as the power of g. So and another way to describe a primitive root is as follows. Let's say that b, or in general, g is a primitive root mod m if and only if the order of g mod m, that is the smallest positive power of g equal to 1, is phi of m. So suppose b is relatively prime to m, then b is congruent to g to the k mod m for some k. Suppose we let, I don't know, L be the order of b. That means b to the L is congruent to 1 mod m, but of course b is g to the k, so that's the same as saying g to the k times L is congruent to 1 mod m. Right? All right. So the idea is take one primitive root mod m. We're told g is a primitive root. So for that g, every congruence class or every integer relatively prime to m is congruent to a power of g. Plus b has some order. Let's call the order L. So b to the L is congruent to 1 mod m, and L was the smallest integer with this property. But b is g to the k, so that's the same as saying g to the k L is congruent to 1 mod b, mod m. So another way of saying this is, if b is congruent to g to the k mod m, b is a primitive root, another primitive root, mod m, if and only if L is the smallest integer such that g to the k L is congruent to 1 mod m. Right? So b is g to the k, and b has order L, and it's a primitive root. Let me say this a little bit better. So every non-zero, every integer relatively prime to m is of the form g to the k mod m, or is congruent to g to the k mod m for some k between 1 and phi of m, because the phi of m powers of g give you all the congruence classes relatively prime to m. And g to the k is a primitive root. So you don't have to look at numbers b, you just have to look at powers of g of k, powers of g. G is a primitive root if and only if g to the k has order phi of m mod m. So if and only if phi of m is the smallest positive integer L such that g of k times L is congruent to 1 mod m. So maybe we should just divide our problem up into two cases. So in the first case, k and phi of m have a greatest common divisor 1. And in case 2, the greatest common divisor of k and phi of m is some number d, which is not 1, so it's at least 2. Okay? So in case 1, g to the k times L is congruent to 1 mod m, if and only if, this is always the case, KL is a multiple of phi of m. It's congruent to 0 mod phi of m. And if k and phi of m are relatively prime, if phi of m divides k times L, and k and phi of m are relatively prime, then L is congruent to 0 mod phi of m, which means L equals phi of m, which means g to the k is another primitive root. Mod m, right? So every number we look at is g to the k for some k. If k is relatively prime to phi of m, KL is divisible by phi of m if and only if L is divisible by phi of m, which means g to the k is a primitive root. So k phi of m equal 1 implies g to the k is a primitive root. In the second case, the greatest common divisor of k and phi of m is d, which is bigger than 1, at least 2. So, and also, so phi of m over d, this is an integer. It's a positive integer, which is strictly smaller than phi of m. So if I take g to the k and raise it to the integer, positive integer power, phi of m over d, this is g to the k phi of m over d. This is the same as g phi of m times k over d. And k over d is also an integer. So this is g to the phi of m raised to the power k over d. But g to the phi of m is congruent to 1 mod m, which is 1. So in this case, phi of m over d is an integer smaller than phi of m. And if I raise g of k to that power, I get 1. So g to the k does not have order phi of m. It has a smaller order. So in fact, g to the k is a primitive root if and only if k and phi of m are relatively prime. And the number of k between 1 and phi of m, such that k and phi of m are relatively prime, this is just phi of m. By definition, this is the number of integers positive up to phi of m that are relatively prime to phi of m. So that's a proof that the number of primitive roots is phi of m. So this takes a little bit of work to, go through the proof step by step and understand what's going on. But when you succeed, then you'll have a very nice understanding of the meaning of primitive root.
Professor, can you center the paper?
Center it. Is that centered?
No, just like the bottom portion wasn't able to be seen. That's all. Thank you.
Oh, okay, sure.
This is problem 11 of what chapter?
This is problem 11 of section 3.1. That's a nice problem. You have to think about it for a while, I think. Other questions you might like me to go over? Otherwise, I'll just pick some from maybe a different section.
Professor, I wouldn't mind section 3.4 to do some questions, but if everybody's done with 3.3 or 3.1, I should say, sorry.
Well, section 3.4 is good. That has to do with quadratic residues. Section 3.4, and no reason not to start with number 1. So we want to solve two congruences, x squared congruent to 2 mod 47 and x squared congruent to 2 mod 53. Sorry, the problem says find all solutions. Maybe there aren't any. Huh. So, of course, we did prove the theorem in this section, which says for an odd prime p, the Legendre symbol 2 over p is 1 if p is congruent to plus or minus 1 mod 8, and minus 1 if p is congruent to plus or minus 3 mod 8. So let's look at the congruence mod 8, the congruence class mod 8 of each of these primes. 47 is congruent to minus 1 mod 8. So 2 over 47 is plus 1, which means x squared congruent to 2 mod 47 has two distinct solutions. Mod 47. What about 53? 53 is congruent to minus 3 mod 8. So 2 over 53, that Legendre symbol is minus 1, which means x squared congruent to 2 mod 53 has no solution. So we solved the problem for this congruence. Find all solutions, answer the empty set. There is none. All right. So we can stop with this. And to solve this, well, there's one obvious solution, namely, because you just look at squares, and 7 squared is 49, which is congruent to 2 mod 47. And minus 7 squared is also 49, which is congruent to 2 mod 47. So plus or minus 7, or if you want a positive solution, minus 7 is the same as 40. So 40 squared is also congruent to 2 mod 47. So for x squared congruent to 2 mod 47, the smallest positive solutions are 7 and 40. Let's just check so we know that everything is right in the world. 40 squared is 1600. 1600 minus 2 is 1598. And if you divide 47 into 1598, let's see, this goes 3 times, 3 sevens are 21, 3 fours are 12, 14, 8, 8, 1. And 47 goes into this, I think, 4 times. 4 sevens are 28. Perfect. So this number is congruent to 0 mod 47. So 40 squared minus 2 is congruent to 0 mod 47. So 40 squared is 2. So in any case, the answer is for the first congruence, there are 2 solutions, 7 and 40. For the second congruence, there is no solution.
Professor, can you just quickly repeat why there's no solution for 53?
Yes. So we proved the following theorem. 2 over p is the Legendre symbol. It's 1 if 2 is a quadratic residue mod p, and minus 1 if 2 is not. So we proved the theorem that the Legendre symbol 2 over p is 1 if p is congruent to plus or minus 1 mod 8, and minus 1 if p is congruent to plus or minus 3 mod 8. So the prime 53 is congruent to minus 3 mod 8. That means the Legendre symbol 2 over p is minus 1. This means this congruence has no solution. Right?
Got it, thanks.
I mean, theorems are, valuable. No, these are fun.
Professor.
Look at it. That's a
Professor.
good problem too. There any questions about this?
I have a question really quick.
Yeah, go ahead.
How do you pick 40 as the second solution? What was the logic behind picking 40?
Oh, well, did you see that 7 was the solution?
Yes.
But you're squaring. So if 7 squared is 49, minus 7 when you square it is also 49.
Okay.
Well, that's it. So minus 7 is not, minus 7 is different from 7. And mod 47 minus the same is the same as 40,
Okay, I get it.
right? It's just like in, high school when they say, solve the equation x squared equals 1. And you can say, well, x equal 1 is a solution, but x equal minus 1 is also a solution, right? Because you're just squaring. When you square a squared and minus a all squared is still, they're both a squared. So when you're solving these quadratic congruences, once you find one quadratic residue, the other one is always minus the first, because there are only 2 solutions, and if you have one, the negative is a different one. So finding two solutions is the same as finding one solution, because in the sense that once you find the first, the negative is just gives you the second solution. Let's look at number 2 in the same section. Prove that S equal to 3, 4, 5, 9, and 10, those 5 positive integers, is a Gaussian set mod 11. So you have to remember, what is a Gaussian set? It's a set of numbers with the property that the numbers together with their negatives gives you a complete set of representatives of the non-zero congruence classes mod P. So if this is S, what is minus S? It's minus 3, it's just the negatives, minus 4, minus 5, minus 9, and minus 10. So if we look at the congruence classes A mod 11, the non-zero ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 3, and this is an element in S union minus S. So 3 is in S. 4 is in S. 5 is in S. 9 is in S. And 10 is in S. But what about 1? 1 is the same as minus 10, which is in minus S. 2 mod 11 is the same as minus 9. That's in minus S. 6 is the same as minus 5. That's in minus S. 7 is the same as minus 4. That's in minus S. 8 mod 11 is the same as minus 3. That's in minus S. So every congruence class mod 11, not 0, is congruent to an element in S or negative S. So this is a Gaussian set, right? That's the proof that it is a Gaussian set. And the interesting part of the problem is to use Gauss's lemma to compute the Legendre symbols 3 over 11 and 7 over 11. So what Gauss's lemma says is the following. If you have an integer a relatively prime to p, for every s in the set capital S, a times s is going to be plus or minus some element of s. So you can write as epsilon a of s, u sub a of s, where this epsilon sub a is plus 1 or minus 1, and u sub a of s is an s, and the Legendre symbol a over p is equal to the number of minus 1s. It's the number of s and s where epsilon sub a of s is minus 1. Sorry, it's if you let m be the number of minus 1s as s runs through all the elements of the set S, a over p is minus 1 to the m. Right? So that's what Gauss's lemma says. So we want to apply this to the prime p equal to 11. And in the first case, a equal to 3. So we have to compute 3 times 3 3 times 4, 3 times 5, 3 times 9, and 3 times 10. So 3 times 3 is 9, which is already an S. So that's 1 times 9. Mod 11. 3 times 4 is 12. 12 is the same as 3. Mod 11. 3 is in the set S. That's 1 times 3. 3 times 5 is 15. Mod 11, that's the same as 4. That is also in the set. 1 times 4. 3 times 9 is 27. 27 mod 11 is 5. Oh, we're lucky. This is 1 times 5. Mod 11. 3 times 10 is 30. Mod 11, this is 8. 8 is not in the set, but 8 is congruent to minus 3. So this is minus 1 times 3 mod 11. So we look at the plus or minus ones. How many are equal to minus 1? Just one of them. So M is minus 1. So that says that 3 over 11 is equal to minus 1. Minus 1 to the 1. Sorry, M is equal to 1. There's one negative number. So this is minus 1 to the 1 or minus 1. So 3 is not a quadratic residue mod 11. So there's no reason to look for it, to start squaring numbers to see if you get 3. By Gauss's lemma, we know 3 is not a quadratic residue mod 11. Okay. The second part of the problem was to use Gauss's lemma applied to the number 7. So our Gaussian set is 3, 4, 5, 9, and 10 with respect to the prime 11, and we're taking the number A equal to 7. So we have to look at 7 times 3, 7 times 4, 7 times 5, 7 times 9, and 7 times 10. 7 threes are 21. 21 is the same as 10 mod 11. 10 is in the set. That's 1 times 10 mod 11. Everything is mod 11. 7 times 4 is 28. Mod 11, 28 is the same as 6. 6 isn't in the set, but 6 is congruent to minus 5. That's minus 1 times 5 mod 11. So here we got a plus 1, here we got a minus 1. 7 times 5 is 35, which is congruent to 3 mod 11. 3 is in the set. This is 1 times 3. So here we get a plus 1. 7 times 9 is 63. Mod 11, that's the same as 8. 8 is not in the set, but 8 is the same as minus 4 or minus 1 times 4 mod 11. So here we got a minus 1.
Professor,
Yeah.
35 is not congruent to 2 mod 11.
Oh, I'm sorry. 35 is congruent to 33 is congruent to 2. Thank you. Good. That's congruent to 2. 2 is not in the set, but 2 is the same as minus 9 or minus 1 times 9 mod 11. So this is a minus 1 here. Let's see, 55 plus 8, that's okay. And 8 is -3. 8 is not in the set, but this is -3, which is -1 times 3. So I got a -1 there. And 7 times 10 is 70, which is congruent to 4 mod 11, or 1 times 4 mod 11. So here we get a +1. So how many -1s are there? 1, 2, 3. So m is equal to 3, and the Legendre symbol 7/11 is -1 cubed, which is -1. So 7 is not a quadratic residue, mod 11. And just to double check, what are the quadratic residues, mod 11? Well, they're the squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, which is 5, 5 squared is 25, which is 3. And 6, 7, 8, and 9 are just the negatives of these. So the quadratic residues modulo 11 are 1, 3, 4, 5, and 9. Oops. So I made a mistake over here, right? What's wrong over here? Because I think over here, I said that 3 was not a quadratic residue, mod 11, but it is. I'm glad I checked. Let's see, 3 times 3 is 1 times 9. 3 times 4 is 1 times 3. 3 times 5 is 1 times 4. 3 times 9 is 27. 27 is 5. Which is 1 times 5. 3 times 10 is 30, which is 8, which is -1 times 3. So m is 1. So this definitely says 3 is not a quadratic residue, but 5 squared is congruent to 3. So something is wrong. What is wrong? 3, 4, 5, 9, and 10. 3 times 3 is in the set. 3 times 4. I can't do arithmetic. 3 times 4 is 12. 12 is the same as 1 minus mod 11, not whatever I wrote. 1 is the same as -10. -1 times 10. So m, in fact, there are 2 -1s. So m is equal to 2. And the Legendre symbol 3/11 is -1 squared, which is +1. So it's always good to check as much as you can. And when I did my check to find the quadratic residues, 1, 3, 4, 5, and 9. Not 7, but 3 is definitely a quadratic residue. Ooh, glad I did that. Any questions? Okay. Everyone makes mistakes, but the more you check, the safer you are. Number 3 is when you have an odd prime p, is to prove that the set of all the even numbers, 2, 4, 6, 8, 10, and so forth, up to p-1, is a Gaussian set. So we could write this like this. If p is, let's say, 2k plus 1, this is the set 2 times 1, 2 times 2, up to p minus 1 is 2 times k. This is just the even numbers. 2i. I goes from 1 up to k. What are the numbers that are missing between 1 and p minus 1? It's the odd numbers. So this is my set S. Minus S is the set minus S, S and S. That's the set of numbers minus 2i. I goes from 1 up to k. Modulo p, this is the same as 2k plus 1 minus 2i. I goes from 1 up to k. That is, the number 2k plus 1 is congruent to 0 mod p, mod 2k plus 1. So this set of numbers represent exactly the same congruence classes as these. What is this? This is 2 times k minus I plus 1. I goes from 1 up to k. As I goes from 1 to k, these numbers go from k minus 1 down to 0. I can write this as 2j plus 1. J goes from 0 up to k minus 1. So this is just the set of numbers 1, 3, 5. When j is 2k minus 1, I get is k minus 1, I get 2k minus 2 plus 1, 2k minus 1. Sorry, 2k minus 2 plus 2k minus 1. Yeah. So if I take the numbers, the even numbers up to 2k and the odd numbers up to 2k minus 1, S union minus S in terms of the congruence classes is everything up to 2k, which is everything from 1 up to p minus 1, all the non-zero congruence classes mod p. So that's a proof that if I take the even integers between 1 and p, I always get a Gaussian set. Any questions about this? I mean, this is a little bit harder mathematics. We're using everything we've done so far. In problem number 4, we want to use two theorems, 3.14 and 3.16, to find all the primes for which minus 2 is a quadratic residue. That means all the primes for which this Legendre symbol is equal to minus 1. So what do these two theorems say? 314 tells us when minus 1 is a quadratic residue, it's equal to 1 if and only if p is congruent to 1 mod 4. Every prime is either 1 or 3 mod 4, every odd prime. And it's only the primes for which for which p is 1 mod 4, for which minus 1 is a quadratic residue. And 316 tells us when 2 is a quadratic residue, if and only if p is congruent to plus or minus 1 mod 8. So how do we calculate the Legendre symbol minus 2 over p? Well, mod 8, every prime is either 1, 3, 5, or 7. Mod 8. 5 is the same as -3, and 7 is the same as -1. Right? So in each of these 4 cases, and we use the fact that the Legendre symbol is multiplicative. So -2 over P, -2 is -1 times 2 over P. So this is -1 over P times 2 over P. So let's look at all the cases. Suppose P is congruent to 1 mod 8. In that case, P is also congruent to 1 mod 4. So -1 over P is 1. 2 over P is 1, and 1 times 1 is 1. So if P is congruent to 1 mod 8, the Legendre symbol is 1. Suppose P is congruent to 3 mod 8. That means P is also congruent to 3 mod 4. So if P is congruent to 3 mod 4, -1 over P is -1. 2 over P, P is congruent to 3 mod 4 mod 8. This is also -1. We get a +1. What happens if P is congruent to 5 mod 8? Well, 5 mod 8 implies 5 mod 4 or 1 mod 4. So this Legendre symbol is 1. And 5 mod 8, this Legendre symbol is -1. And the last case is when P is congruent to 7 mod 8, which means P is congruent to -1 mod 8. P is also congruent to 3 or -1 mod 4. So this is going to be -1. This is going to be +1. We get -1. So we proved our result. -2 over P. 2 is a quadratic residue. Mod P. This is equal to 1 if P is congruent to 1 or 3 mod 8, and -1 if P is congruent to 5 or 7 mod 8. So this is a calculation using the Legendre symbol. It tells us exactly for which primes -2 is a quadratic residue. So for example, if you take the prime 19, 19 is congruent to 3 mod 8. So -2 over 19 is 1. -2 is a quadratic residue. X squared congruent to -2 minus 19 must have a solution. And in fact, 6 is a solution, right? Because 36 plus 2 is 38, is 2 times 19. Good. This is just an example of the use of the exercise we just proved.
Professor, can you show the bottom part, please?
Sorry?
Can you bring the paper a little bit up?
Like this?
Yes, thank you.
Sure. Oh, let's look at number 5. So problem number 5 is to use Gauss's lemma to find all primes P for which -2 is a quadratic residue. So we already know from problem 4 what the answer is. In problem 5, we're just supposed to solve the same problem by a different method using Gauss's lemma. So in Gauss's lemma, you have to start with a Gaussian set, and I have no idea what Gaussian set to choose. So maybe I'll start by choosing the simplest one I can think of. So let's try the Gaussian set S equal to just the first P minus 1/2 integers. So I want to compute. So for every S in this set, I write -2S as some plus or minus 1 times some element of S, and M is equal to the number of S in the Gaussian set, where we get a -1 there instead of a +1. Okay, any questions about how we're starting to do the problem? Now, if you look at the proof of theorem 316 using a Gaussian set, it took a little bit of work. There were different cases to consider. So
Professor, so is epsilon equal or not equal to 1?
it depends on which element S from the Gaussian set you're choosing. So for example, let's just start to do some calculations. So what's epsilon -2 of 1? That's -2 times 1, or -2. That's -1 times 2. So this epsilon in this case is -1. Epsilon -2 of the number S is -2S. This is -1 times 2S if 2S is between 1 and P minus 1/2, right? Because if 2S is between 1 and P minus 1/2, it's some element that's already in S. So in this case, U minus 2 of S is -1. And sorry, epsilon minus 2 of S is -1. And U minus 2 of S is 2S. So epsilon minus 2 of S you get a -1 for S in this interval, or equivalently, if S is less than P minus 1 over 4, and S has to be positive, of course. So for S between 1 and P minus 1 over 4, I get a -1. Suppose P minus 1 over 4 is less than S, is less than or equal to P minus 1 over 2. Then minus 2S, if I multiply by -2, this is greater than or equal to minus P minus 1 and less than minus P minus 1 over 2. Right. I have to take each of these numbers, multiply it by -2, and then that's always going to be equal to plus or minus something in this set. So if S is between 1 and P minus 1 over 4, when I multiply by -2, I get something between -2 and minus P minus 1 over 2. It's going to be the negative of one of these. So if S is between 1 and P minus 1 over 4, 2S is between 1 and P minus 1 over 2, minus 2S is between minus this and -1. So it's the negative of one of these. So I'm going to get a -1 for all the S's between 1 and P minus 1 over 4. The other S's in this set are bigger than P minus 1 over 4 and less than or equal to P minus 1 over 2. If I multiply by -2, minus 2S is bigger than minus P minus 1 and less than minus P minus 1 over 2. So minus 2S less than minus P minus 1 over 2 greater than or equal to minus P minus 1. If I want a number congruent to this modulo P, I can always add P. So mod P minus 2S is between P minus 1 over 2 and P minus 1. That means minus 2S mod P is less than, this is P plus 1 over 2, and this is 1. A number is less than P plus 1 over 2 is the same as being less than or equal to P minus 1 over 2. So in this case, minus 2S is congruent to plus an element of S, because everything between 1 and P minus 1 over 2 is in this set. So the number of negative ones is the number of S's between P minus 1 over 2. So if I take S equal to 1, 2, 3 up to P minus 1 over 2 and A equal to -2, the number of M's, the number of S in S, such that epsilon to -2 of S is equal to -1, is the number of integers S between 1 and P minus 1 over 4. And this number is going to depend on the congruence class of P mod 8. So if P is congruent to 1 mod 8, means P is a number of the form that say 8L plus 1. So P minus 1 over 4 is 8L over 4 is 2L is even. So the number of integers in this set is even if P is congruent to 1 mod 8. Suppose 3 is congruent to 3 mod 8. So P equals 8L plus 3. So P minus 1 over 4 is 8L plus 2 over 4. That's 2L plus a half. The number of S such that 1 is less than or equal to S is less than or equal to 2L plus a half. If it's an integer, is 2L, which is also even. So in this case, M is also even. What if P is congruent to 3 mod 8? So P equals 3L plus 8. So P minus, 8L plus 3. So P minus 1 over 4.
Professor,
is
you just
8.
did that.
Sorry,
You
this
just
should
did
be a
that.
5. This is the case, P congruent to 5 mod 8. So P is 8L plus 5. So P minus 1 over 4 is 8L plus 4 over 4, which is 2L plus 1, which is an odd number. And if P is congruent to 7 mod 8, then P equals 8L plus 7. So P minus 1 over 4 is 8L plus 6 over 4. That's 2L plus 1 plus a half. The number of integers from 1 to 2L plus 1 over 2L plus 1 plus a half is 2L plus 1. It's odd. So we get that minus 2 over P equals 1 precisely when M is even. If P is congruent to 1 or 3 mod 8, and minus 2 over P is minus 1, whenever we are in the odd case, and that means P is congruent to 5 or 7 mod 8. So we recovered exactly the result we had obtained by a different method in the previous problem. So things are always good in the world when you can solve a problem 2 ways but get the same answer. All right. Any questions about this? Let me do at least one problem from section 3.3 on power residues. So not just quadratic residues. So problem number 1 is find all cubic residues modulo the prime 19. That is, find all integers A such that x cubed congruent to A minus 19 has a solution. A relatively prime to 19. So the simplest thing is just to start by looking at the cubes mod 19. 1 cubed is congruent to 1 mod 19. 2 cubed is congruent to 8. 3 cubed is 27 which is the same as 8 mod 19. 4 cubed is 64. Let's see, mod 19. 3 times 19 is 57. So this is 7 mod 19. 5 cubed is 125. Let's see, 125 is, let's see, 6 times 19 is 114, I think. So maybe this is 11. Yeah, 5 cubed is 11 mod 19. 6 cubed is 216. Let's see, what is that mod 19? 19 into 216.
Seven.
7. Huh. Okay. Ooh. What about 8 cubed? No, sorry. What about 7 cubed? 7 cubed, I think, is 343.
Yes.
And if you divide 19 into
1.
3,
That one is 1 mod 19.
sorry,
1 mod 19.
it's congruent to 1?
Yes.
Okay. I believe you. 8 cubed. Huh. Ooh. That's 2 to the 6th. No, 2 to the 9th. That's 512. If you divide 19 into 512, what do you get?
Congruent to 18.
18. Okay. What about not? Let's see. So far, what numbers do we have? We have 1 is a cubic residue, 8 is a cubic residue, 7 is a cubic residue, 11 is a cubic residue, 18 is a cubic residue. Huh. What about 9 cubed? That's 729. If you divide 19 into 729, that goes, and also, I think you also get 7.
Yes.
Okay. 10 cubed is 1,000. 19 into 1,000. I think you get 12.
Yes.
At least we found another. Of course, we still have to track 11, 12, 13, 14, 15, 16, 17, and 18. Huh. But if you do, I think what you will find is you won't find any new cubic residue. And every number that, and in this particular case, if A is a cubic residue, this congruence actually has 3 different solutions. So there are 18 congruence classes mod 19, but exactly 6 cubic residues. 1, 7, 8, 11, 12, and 18. Those are the cubic residues. Of course, there's 1 cubic residue that you always get, which is, because 1 cubed is 1, 18, which is -1 mod 19, So 18 cubed is minus 1 cubed. You're always going to get plus or minus 1 as cubic residues. And this is the same as minus 1. But the hard ones to find are all the others. And in this case, mod 19, there are only 6 cubic residues. But sometimes, and the most you can have is p minus 1. Sometimes you actually see that every number is a cubic residue. That's very interesting. So cubing the numbers is just a kind of a permutation. Yeah. It's all very interesting. If you have the time, and it's nice to spend a few hours with pencil and paper, just calculating quadratic residues and cubic residues and just seeing what numbers occur and how many times they occur. Quite interesting. Okay. Any questions about any of this? I do have office hours, Zoom hours, if you like, Monday, Tuesday, and Wednesday of this week at different times. So welcome to log on at any time. When we, yeah. And I think on Wednesday, according to the syllabus, we proved the quadratic reciprocity law, which is the most important result in the course and the most difficult. But and then there's Thanksgiving. Monday there's a review, and a week from Wednesday is the second exam. So on December 1st. So good to keep that schedule in mind. Okay. Any questions about anything we did today or any other questions on number theory? Okay, if not,
Professor,
yeah,
you will send a review like the last exam for us to study before the exam?
yeah, I will send out a review set for the exam.
Okay, perfect. Thank you.
Yeah, okay. Other questions?
Professor, do you think that it's possible to send it before Monday so we can start working on that and reviewing?
I'm sorry, I didn't hear what you said.
If you think that it's possible to send the exam review before Monday so we can start practicing and reviewing.
Okay, I'll make sure I send it out. If you don't have it by Wednesday morning, just remind me.
Okay, thank you.
Okay, but I'll try to send it out today or tomorrow.
Thank you.
Okay. All right, all. See you on Wednesday. Bye-bye.
Have a
Thank you,
nice day.
Professor. Bye.
Have a good one, Professor.
Thank you.